to the GATE Academy again. So this is the last session in our live series of steam turbine and gas turbine. Okay. So before this session, we already have completed 11 sessions on this, and this 12th session is going to be the last session in this live series of steam turbine and gas turbine. And as you know, it is the recently added topic. As you know, it is our recently added topic in GATE 2021 syllabus. Okay. So we are again meeting here for concluding our steam turbine and gas turbine part of thermodynamics, which has been added in GATE 2021 syllabus. All right. So firstly, let me introduce myself. So who am I? Who am I? So as you can see on the screen here, our continuing topic is, this is the last session. This is the last session of this topic. This is the last video on this topic, steam turbine and gas turbine. If you want to understand it completely, you can subscribe the GATE Academy channel. You can subscribe the GATE Academy channel, the GATE Academy English channel, and there you will have all the 11 sessions with you. Okay. So my name is Umashankar Tripathi. My name is Umashankar Tripathi, and currently I am a PhD scholar at IIT Roorkee. PhD scholar that you guys usually call as research scholar as well. Okay. So you can say I am a research scholar, PhD scholar, IIT Roorkee, in IIT Roorkee. So it's the same thing only. Okay. So before getting into this PhD program in IIT Roorkee, I completed my MTech from IIT Roorkee itself. So for taking admission in this Master's MTech program, you all are aware that we have to qualify the same examination for what you are preparing for. So I have qualified the GATE 2014 examination and had 65.66 marks, obviously out of 100. And achieved All India rank of 916. On the basis of this rank, I took admission in IIT Roorkee MTech program. Okay. Okay. In GATE 2015, I had this much marks, and All India rank of mine was 643. 643 was my All India rank. Okay. So I have a teaching experience of 8+ years. I have a teaching experience of 8+ years. From more than 8 years, I have been into this teaching the experience for the GATE examination. As you know, the GATE Academy is having 50+ centers, 50+ offline centers, 50+ physical centers, you can say, across various cities in India. Okay. So before this Corona thing, we used to travel and in different cities and teach the aspirants. Okay. Okay. So as we have covered, this is a brief introduction because this is the last session, last video of this session. So let me quickly go to what is required. So we have completed everything, all of this in the previous session. In the previous session, we have completed the ideal Brayton cycle. And in this session, actual gas turbine cycle was pending from the previous session. So in this lecture, we will be completing the actual gas turbine cycles, and as well as we will have a brief discussion. We will have a very brief discussion of the components of gas turbine cycle as well. Components of gas turbine cycle as well. So just let us quickly go to our discussions. Let us quickly go to our discussions. So now we have completed till this point in the previous session. We have completed the ideal Brayton cycle. We have completed the ideal Brayton cycle in all possible respects. We have completed the ideal Brayton cycle in all possible respects. We have seen the ideal Brayton cycle. Then we have seen some terms like work ratio, back work ratio, and all. Then we have derived the equations and the conditions in which we get the maximum work output, what efficiency we get at the maximum work output condition. We have done all that. Then we have seen the cases of regeneration, intercooling, and reheating individually. And finally, we have combined it all. And lastly, we have seen this question. And in this question, everything is combined. Intercooling, reheating, everything is combined. Everything is combined. And we have solved this question. So now let us move. Why we were studying this ideal gas turbine cycle in all the respect, because we wanted to learn the actual gas turbine cycle. So as gas turbine, now see what I am thinking. See, in gas turbine portion, when in GATE it is written that steam turbine and gas turbine portion. So gas turbine is same as what we have seen is steam turbine sessions. Okay, you can see the previous session. So we have discussed about impulse turbine, we have discussed about reaction turbine, we have seen the velocity triangles, we have developed expressions, so many expressions for efficiency, in this case, that case, types of turbines. So everything we have seen already. So gas turbine as an equipment, we have already covered in steam turbine sessions, in a steam turbine section. Okay. Gas turbine bleeding is kind of similar to what we learned in a steam turbine. Everything is almost similar. Even there is a topic in previous GATE syllabus, that is compressors. So there you see axial compressors, axial flow compressors, and as I told you in the steam turbine section, that our steam turbine is also an axial flow turbine, and same stands for the gas turbine. Gas turbine is also an axial flow turbine. It's also a completely axial flow turbine. Okay, so everything what we have learned in the steam turbine, every calculation you can put in the gas turbine section also. So it is not necessary to go for it again, see all those nozzles, compressible flow, everything. So if you want to know about it, do subscribe the channel, go and watch the previous sessions also. Okay. So now, according to me, when they written gas turbine, so what is extra? What is left? So they can ask GATE examination, maybe they may ask about the actual gas turbine, which we usually do not take very much seriously while preparing the general syllabus of GATE examination, which was previously added syllabus. As if some of you who has already completed the power plant of old syllabus, you must be understanding this. That's an ideal cycle was already there. Regeneration was already there. Reheating was already there. Intercooling was already there. Okay. So previous session was almost about whatever was that was already there. But why we have learned it here? So as we can completely use those concepts what we have already learned in the case of actual gas turbine. Now, if I explain the actual gas turbine cycle, so by the name itself, it is very much clear. By the name itself, it is very much clear that now practical things will come into picture. The ideal things won't no more play its role, will not anymore going to play its role. Okay. So we have seen in ideal cycle, we have seen some air standard assumption. So in actual gas turbine cycle, what can happen? Some of those assumptions could not no more hold good, or some of them may hold good, some of not may not have hold good. So some can be valid, some of them can be valid in a question, some of them cannot be valid in the question, may not be valid in the question. Okay, a combination of them may be valid, maybe all of them not valid. So how to deal with this actual gas turbine? We are going to have this discussion mostly in this session. Okay, so first is, let's say CP CV gamma. We have seen one assumption in the previous session that CP CV gamma do not change with temperature. Live students can respond to me. Have we seen it or not? CP CV gamma do not change with the temperature. This is the air standard assumption we considered while discussing the ideal Brayton cycle. Is it or isn't it? So this is the assumption for the ideal cycle. So if I want to go to the actual cycle, this may change with temperature. This may change with temperature. Okay. Okay. So actual gas turbine cycle, if Cp, Cv, gamma change with temperature, then how to do it? How to do it? What will be the changes happen in your analysis? What will be the changes happen in your analysis and in your formula? So just see here. Just see here what will happen. Just see here. So firstly, from the classical thermodynamics, we must have this understanding that with the temperature, what happens? With temperature, what happens? With the increase of temperature, Cp increases. With the increase of temperature, Cv also increases, but gamma decreases. But gamma decreases because gamma is nothing but the ratio of Cp by Cv. So simple mathematics, if any fraction greater than 1 is greater than 1 and both the numerator and denominator both will be increasing, then the fraction value will be reduced. Then the value of the fraction will get reduced. Value of the fraction will certainly going to get reduced. All right. All right. So what will be the effect? What will be the effect? What will be the effect of these changes? What will be the effect of these changes? What will be the effect of these changes in our gas turbine, ideal gas turbine cycle may occur. So for that, we will do something like this. Now see, this is our ideal gas turbine cycle as we have know it as we know it. So this is our ideal gas turbine cycle. Okay. Okay. So if CPCV gamma is changing, CPCV is gamma is changing. So we do not consider the changes while flowing through 1 to 2, but we consider the changes when combustion chamber thing happens. When combustion chamber thing happens, quite obviously, while this air flows or while this gas flow or while this system or steam or fluid flows through the combustion chamber, its temperature increases to a greater extent because combustion chamber is the place where you add heat into it, So most of the increase of temperature, takes place in this combustion chamber part. That is why we consider this happening before combustion chamber state and after combustion chamber state. So before combustion chamber state, let me say the properties were, or these value was Cp, Cv, gamma, So after at this 3 point, so let's call it air. Let us call it air. Okay. So I'm writing it here. Just try to understand the concept. You have to pay some attention here. See, these are some things which are very easy to understand only when you listen properly. Okay, otherwise you will definitely going to make some mistakes in it. So in order to avoid those mistakes, that is why we have seen the ideal cycle. We will apply the concept of actual cycle in the existing concept of ideal cycle so that not much changes will happen in your understanding. So now see. So here we have Cp, here we have Cv, and here we have gamma. So I will call it as air. Okay. Okay. But when this air flows through this combustion chamber, goes through combustion chamber due to such high changes of the temperature, we can say now the properties had changed and I will call it gas. No more it will be air, it will be gas because the Cp, Cv and gamma value would have been changed. So I will call it as Cpa, Cva, gamma A. Here we will use Cpg, Cvg and gamma G. So this also happens because in combustion chamber, practically what happens in combustion chamber till now in ideal cycle, we have been considering this fact. We have been considering that whatever fuel has been burnt in combustion chamber, just by naming the combustion chamber, you understand this, that the temperature or heat addition, temperature increase or heat addition won't happen. You have to burn something, you have to burn some fuel. and that heat energy of the fuel will go to the air, and hence the heat will be added in the air. And by that process, the heat will be added into the air. All right. So when fuel burns, some part of it, we consider that some part of it or the entire fuel mixes with, that is, we are going to see that in the combustion chamber. So mass flow rate also changes. Here, if the mass flow rate is m dot a, at this place the mass flow rate will change to be m dot a plus m dot f, m dot a plus m dot f, because certain amount of these gases of this fluid of the fuel is also get added with the mass flow rate of air. So here the properties, the specific heat, the value of gamma may change at this condition before the air. So if CPCV gamma, if CPCV gamma, if CPCV gamma changes, if CPCV gamma changes with respect to temperature, your properties of the gas may change. And if this will happen, now don't get confused, let me delete it if you are getting confused. Okay, we will consider it when we see the combustion chamber. So just take it into your mind also that as the combustion chamber, in combustion chamber some fuel is getting heated, so that of that mass is also going to get mixed with some air. Okay, mixed with air. So at this 3 point, if we consider that also, the combustion chamber thing also, so the mass flow rate will also increase. So I think, is it clear till this point? If CPCV gamma changes, what you have to do when you call it a air, when you will call it a gas, So let's try to understand this with the second variation of combustion chamber. So what happens in combustion chamber? Let's see that. So we may call it, we are dealing with the actual cycle now. So combustion chamber. Okay, so what happens in the combustion chamber in general? So combustion chamber, what happens? The system or the air leaving the compressor at 2 enters the combustion chamber, and leaves at 3. So what we have seen till now in the ideal cycle is heat added is equal to m dot a T3 minus T2. This is for ideal cycle. We do it for ideal cycle. So for ideal cycle, till now we have been using this only. That's every time heat added we use as m dot a T3 minus T2. But in actual conditions, But in actual condition, what happens? What happens? Whatever fuel you are burning. So in ideal condition, what we have considered, let's first talk about it. So in ideal cycle, you have observed in the previous session that we have been using this heat added. So what we were assuming there, that whatever fuel has been burnt, and given the energy released by burning, so this LCV is what we call lower calorific value. You know the calorific value? So we generally use lower calorific value. Yes or no? Lower calorific value is the part of energy that can be actually utilized. So this is the lower calorific value. So we say that this lower calorific value and mass flow rate, so whatever heat is being released by the fuel is absorbed by the air, and hence the heat is getting added. Heat is getting added. So till now we have been considering this, but in actual conditions what happens, as you can also understand this, in actual condition what generally happens, that some part of this energy which is released due to the burning of fuel, some part of this energy which is released due to this burning of fuel is wasted in the atmosphere, in the surrounding. So in actual condition, our efficiency called as combustion efficiency will also come into play, which represent the loss of this heat energy before it reaches to the air, before it added to the air, or before it increased the temperature of our air working fluid. Okay, so if what do we mean by this combustion efficiency? If this combustion efficiency is 90%, that means that 10% of the heat energy which is released by the burning of this fuel, which is released by the burning of this fluid, which is released by the burning of this fuel is wasted. So if combustion efficiency is 90%, it means that 90% of the energy has reached or played part in increasing the temperature of this air, of our working fluid. Okay, and if it is 10% means, if it is 90% means 10% is lost. 10% is lost. So if now listen to me very, very carefully. This is a very important point. So if we consider that Cp, Cv, gamma do not change with temperature, if we consider this, that if we see that our first air standard assumption, as we may call it, so Cp, Cv, gamma do not change with temperature. What we can do that, sir, this is the mass flow rate of the fuel. Okay, this is the lower calorific value, and this is the combustion efficiency, because this much is going to reach to our working fluid, that is air. Okay, so we can say Cp, Cv, gamma is not changing. So now we can apply this equation, m dot a Cp T3 minus T2. So what we consider that all this 90% is going to the air and increasing its temperature. So this formula you can use when Cp, Cv, gamma we consider is not changing with temperature. So we call it as approximate solution. Approximate equation or approximate solution, you may call it. So this is approximate. Why we call it approximate? Because this is not 100% reality. This is not exact thing. So we call it approximate solution. So if for you, if actual gas turbine question is asked to you and combustion efficiency is given to you, and Cp, Cv, gamma is given not to be changed with temperature, if nothing is written, how we will know that Cp, Cv, gamma is changing or not with temperature? How we will get this idea? By seeing the question. So if Cp, Cv, gamma changes are not given to you, consider it that it is not changing. So whatever assumptions are violated, you please consider them, and those who are not violated, as like there is an assumption that there is no pressure loss in the ideal cycle. So if in a question nothing is written about the pressure losses, so you consider it that no pressure losses is taking place. Okay. So if Cp, Cv, gamma is nothing is written about it, so you consider our air standard ideal assumptions, and you will use this approximate solution and give the answer. We are going to see some questions on that also. Don't worry. So if if CP gamma, if CP gamma changes, if CP gamma changes with temperature, if CP gamma changes with temperature, if we consider this, then this solution no more holds good, and we have to change our solution like this. We have to write this solution like this, like this. This is the exact solution. This is the exact solution. So you will have this combustion efficiency. So you must write like this, that m dot A plus m dot F, m dot A plus m dot F, CPG. So this is the what? Shruti, this is for mechanical engineering building. This is for mechanical engineering. If you are from mechanical engineering, you can stay here. Otherwise, you can go. So m dot A plus m dot F CPG, m dot A plus m dot F CPG into T3, into T3. So why I am doing this? See here. If CP gamma changes, so here the specific heat at constant pressure we represent by CPG at this 3 states. So we are writing like this: m dot A plus m dot F CPG into T3. As I told you, if this happens, so this we may say that at this point, our mass flow rate also have changed, and now the air has become some sort of a gas in which mass flow rate of air is there, and also mass flow rate of fuel is there. Okay, so minus m dot A minus m dot A CPA T2, m dot A CPA T2. So this is the exact solution. This is the exact solution. I am highlighting it also. This is the exact solution. This is what? This is the exact solution, we may call it. What we can call it? We can call it as exact solution. Okay, because here we have considered, now see here we have the mass flow rate as m dot A. So the temperature is T2, the specific heat is CPA. So we are doing nothing. We are differencing. We are just subtracting the energy at the 3 point minus energy at the 1 point. Energy at the 1 point. Enthalpy difference we are doing again. As I told you previously also, in a constant pressure process, no matter what, we have this formula mCp dt we can use, either whether it is ideal gas or not an ideal gas. No matter. Doesn't matter. Okay. From classical thermodynamics, we get this information. So those who are live can respond to me. Are you able to get this point or not? Where to use exact solution? Where to use approximate solution? When efficiency of combustion is given to you, how to take it? When CP gamma changes with temperature, how to take it? Yes or no? So this is what about the combustion efficiency. So we are going to see the questions of it, but before that, I want to tell you one more thing, and then we will solve some of the questions. And then we will see something else also, and then we will solve a final question. See, mass flow rate are added because we are seeing the actual practical condition. So in practical condition, what happens? This fuel also mixes with, while burning also mixes with in the combustion chamber. Okay. So mostly it happens in open cycle. This fuel mixes with, this mass flow rate of fuel mixes with air, but in ideal conditions we just neglect it, but in actual condition we cannot neglect it. All right. Now moving ahead, so two things we have seen In actual gas turbine cycle, two things, that CP/CV gamma, how to handle that, combustion efficiency, how to handle that, combine both, how to handle that. We have seen it here. Now see, now see, now see. There was one more thing we have considered. There was another thing we have considered while understanding, while studying the ideal cycle, and we have considered that expansion and compression expansion and compression is isentropic. We have seen this assumption as a very standard assumption in ideal gas turbine cycle, but now we are saying expansion and compression is not isentropic, because in actual practice there will be some heat losses. Is it or isn't it? There will be some heat losses. All right, there will be some heat losses in actual. So expansion and compression is not completely isentropic in practical conditions, where there will definitely be some heat losses due to actual working condition. Actual environment will take place. Due to actual working condition, actual environment will take place. So if expansion and compression is not isentropic, then how to deal with it? For that, a term will be given to you as, another term will be given to you as isentropic efficiency. One more term will be given to you as isentropic efficiency. Okay. So if you remember, we have seen something like nozzle efficiency while discussing the steam turbine section. Okay. So it is quite similar to that. So isentropic efficiency we can have of compressor in a question. Isentropic efficiency we can have of turbine in a question. Isentropic efficiency of both can be given in the question. Both can be given in the question. So again, this isentropic efficiency comes into play. When we have a transition from ideal cycle to actual cycle. So this is, you can use not only in gas turbine cycle, but in any cycle where isentropic expansion and compression is taking place. So now what is our ideal cycle? How is our ideal cycle? So let's say we are making TS diagram. So this is our ideal cycle, right? This is our ideal cycle, and this is the pressure line. Now try to understand this. This is going to be used multiple times, and even previously in previous GATE syllabus also this kind of questions are getting asked. Okay, so whenever isentropic efficiency comes into play, then remember two statements of mine. You will never make a mistake in isentropic efficiency. So first statement is, whenever term isentropic efficiency comes, it will be having some losses. So definitely when you go from ideal condition to actual condition, definitely some losses will be there. For sure some losses will be there. Yes or no? For sure there is going to be some losses. In that. Okay. So when we remember the first statement that isentropic efficiency is associated with losses. Now you know from our general thermodynamics concept that whenever losses are there, we are reaching to the irreversibility. And when we are reaching to the irreversibility, in other words, we can say that the entropy is increasing. So if you want to associate the isentropic efficiency with the compressor, just try and increase the entropy. So the entropies in actual process increase. So process must be like this. Because this isentropic efficiency term can be used in case of refrigeration cycles also, in case of Rankine cycles also, in case of any cycle, okay, any cycle. So remember this point, that the isentropic efficiency is associated with the loss. So, so when you do yourself a loss, then your irreversibility increases and your entropy increases. So you have to draw the actual curve. So this is 1 to 2. This is ideal compression. This 1 to 2 represent ideal compression. Okay, and 1 to 2 dash. This red pen 1 to 2 dash represent actual compression, in which you have considered, or you are going to consider, the isentropic efficiency. Okay, in the same way, isentropic efficiency, you have to have it, you have to include it into the turbine part also. So it will associate with some losses, it will give you some losses. So again what will happen? Remember the words of mine, it will give you losses. So irreversibility will increase, so entropy will increase. So if the entropy is to increase from 3 to 4, we will have our 4 dash, somewhere here. We'll have our 4 dash somewhere here like this. Yes or no? Yes or no? So 3 to 4 is our ideal expansion. 3 to 4, you can use this concept in refrigeration also, in Rankine cycle, in any cycle. Okay, so 3 to 4 is our ideal expansion, and 3 to 4 dash is what, when you consider your isentropic efficiency into it, it is actual expansion. So the first point to include the isentropic efficiency into play, into your question or into your analysis, is first thing what you do, you increase the entropy of the process. So when you increase the entropy of the process, when you keep it in your mind, your curve will become light. Okay, is that clear or not? And this is also not a straight line. If you're thinking like that, it is also a curve only, no? It is a curve only. So is that clear till this point? The live student can respond to me. So this is also a curve, okay? Do not get confused. So now our ideal cycle is 1, 2, 3, 4, and our actual cycle is what? 1, 2 dash 3, 4 dash 1. 1, 2 dash 3, 4 dash 1. 1, 2 dash 3, 4 dash 1. Got it or not? Tell me, got it or not? Those who are live can please respond to me. And why I am making it with the dash line? Why I am making it as a dash line? Because you know irreversible processes are represented by the dash line. Okay. So this isentropic efficiency, first statement is clear, that how to draw the curve. Now the second statement of mine here is, whenever you want to see that your efficiency, isentropic efficiency, what it is going to do. So now, as I said that isentropic efficiency comes into play. When some losses are there. And you know beforehand that efficiency is generally less than 1. So when the efficiency is less than 1, you always put the smaller value in the numerator and the greater value in the denominator. Okay. So now think in this way, when we will face the loss in case of compressor. So in compressor, we are required to give the work. We are required to give the work. Okay? In a compressor, the work is given by us. So when we give something, when we are giving something, when loss will come, when we have to give more, when we have to give more. So in case of compressor, can I say, in case of compressor, when isentropic efficiency come into play, in case of compressor, can we say that the actual work of compressor, the actual work, can we say, just wait, can we say the actual work of compressor will be greater than the ideal work, then only we will be in loss, no? That actually what work we require to give will increase. So whenever we talk about the compressor, so compressor efficiency will be ideal work, ideal compressor work to actual compressor work. Got this point or not? Since since actual work is more than ideal work, it must come into the denominator. It must come into the denominator. Mostly, what kind of confusion usually take place? That sir, people say, sir, ideal should be in denominator. No, ideal should be in denominator. No. Why ideal should be in denominator? Because the actual must be more. So in case of compressor, this is opposite. No, because when we are in the loss and we are giving work to the compressor, so when loss will occur, when we are giving more. So in actual condition, we have to give more to the compressor. We have to give more to the compressor, and thereby this compressor efficiency comes into picture. Now let us talk about this turbine efficiency. This turbine efficiency. So with the same fundamentals, can we say, can we say in case of turbine, in turbine now we get work we will obtain. So when the loss will happen, when we obtain less, in general also, when we are giving money to someone, when we will be in loss, when we have to give more, and when we are getting money from somewhere, we are getting money from someone. So when we will be in loss, when we are getting less. So in turbine, this isentropic efficiency will, what loss will happen? That actual work of turbine, what you are actually getting, will be less than the ideal work. Will be less than what? Will be less than the ideal work what you are getting. Will be less than the ideal work what you are getting. So in case of we describe the isentropic efficiency of the turbine, So here actual will be less, actual will be less. So actual turbine work upon upon the ideal turbine work. So here we will put the ratio of actual to ideal, and in case of compressor we will take a ratio of ideal to actual. So don't get confused into it. Just remember those two statements, that always we have to do our loss. So this is very obvious, that when you are giving work, your loss will happen when you have to give more. Okay. Secondly, if you talk about turbine, you are getting work, so your loss will be more. Your loss will be more when you getting less work. So actual work when reduced in turbine, you will be facing some losses, and this will be represented by the isentropic efficiency. So in this diagram, if I want to formulate what is the isentropic efficiency, if I want to write it, so what is the actual? It is ideal upon actual. So we can write T2 minus T1. Okay, or you can say CP T2 minus T1, but CP will be cancelled out, so I have not written it in case of gas cycle. In case of gas cycle, and for this actual you can write T2 dash minus T1. So generally, if compressor efficiency is given to you, isentropic efficiency of given is given to you, you are required to find this T2 dash or vice versa. Or vice versa. T2 dash is generally found from the equation of isentropic efficiency. Similarly, if we talk about turbine, we can write the enthalpy difference. Okay, but as we are talking about the gas cycle, we can directly write. Now here it will be actual by ideal. So what is the actual work we are getting? So actually we are getting from T3 to T4 dash. Actually we are getting from T3 to T4 dash. So it will be actual, and ideally what we needed to get, that is T3 minus T4. So from here generally you are required to find the value of this T4 dash. You are required to find the value of this T4 dash and proceed in the question. So got this or not? Now these three actual components are clear to you. If CP gamma changes with temperature, combustion chamber thing will happen, or 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 if the isentropic efficiency is given in the question, how to deal with all this? Is that clear or not? So we will now do a little bit some of the questions here. So if it is clear, the live students can respond to me. Now. So let's do this question first. Okay, first let's do this question, this gas turbine question. So let us copy this and let us take it there. Where we are studying. So all the students who are live in this lecture can please start solving it. Can please start solving it. We will do 2-3 questions here. Then we will see all the practicalities, and then we will try to apply almost all the practical things. And then we will see a last one more question, and then we will conclude this series. Okay. So our notes of this session, this live series, will be uploaded also on the GATE Academy channel. So again, I am requesting you to please share, subscribe, like. This is all. See, all the new syllabus thing which is covered: gas turbine, steam turbine, everything is covered. So many can get benefits from it. Okay. And in this, at the GATE Academy, as you have observed, if you have seen previous videos also, or if you are seeing this video also, we do not believe in talking more and teaching less. Okay. So in these videos, we are mostly teaching only. This is not the kind of videos you find in which teaching is less and motivation and these kind of things are more. So here we respect your time. Okay, so please subscribe, please refer to other people as well, other students as well. Okay. Now please solve this question. We will have a pause of a minute so that the live students can solve it and can respond to me. If any of you is watching the recorded session, please pause this video here. And do it. Do this question by your own first, then see the solution of it. If you want genuinely good results, if you want genuinely to learn from here, then if you follow this approach, it will be very, very beneficial to you. Just try doing that. Try and do that. So what is it is saying? A gas turbine unit is developed 1500 kilowatt power output. So the power output is developed as 1500 kilowatt. Compressor inlet condition is given to you. Temperature at inlet given to you, and pressure ratio is given to you. So the maximum temperature of turbine inlet is also given to you. Isentropic efficiency of compressor is given to you. Cycle efficiency is given to you, and you are required to find the isentropic efficiency of the turbine. So let's just make the diagram first. So we have again two pressure lines. So let us quickly make the diagram. So this is the ideal cycle. Now see first. Let me conclude here. Let me say something here. So when isentropic efficiency is in place, so we have this 2 dash also. So this blue pen is representing the actual compression, and this blue line here in the turbine section is representing the actual expansion. So what will be the cycle efficiency? If with considering the isentropic efficiency, if we want this cycle efficiency, so cycle efficiency is what? Actual turbine work, definitely. What actual turbine work you are getting minus actual compressor work what you are getting, divided by actual heat addition what is happening, obviously. So what will be the cycle efficiency, my friends? What will be the cycle efficiency here? So what is the actual work done in a turbine? What is the actual work done in a turbine? What is the actual work done in a turbine? So it is, you can see, T3 minus T4 dash, minus what is the actual work of compressor when compressor efficiency is given to you. So that is T2 dash minus T1, upon what is the actual heat added. So now since there is isentropic efficiency come into play, now the actual heat addition takes place between 2 dash and 3, so here we can write T3 minus T2 dash, So in order to get the cycle efficiency, this formula you may use. This is not a formula. We are doing everything with the general concepts. We have having. So for this you require T2 dash, T4 dash, T2 dash. So let's now do the question. So now this cycle efficiency is given to you. So let's just see what we can easily find or given in the question. So P1 is given to be 1 bar. P1 is given to you as 1 bar. T1 is given to you at 293. T1 is given to you as 293 Kelvin. Pressure ratio, that is P2 by P1, is given to you as 6. P2 by P1 is given to you as 6. The maximum temperature of the turbine inlet is given to you as 800. So it is going to be 1073 Kelvin. Just change everything to the Kelvin. So T3 is given to you. And what else is given to you? And compressor efficiency is given to you as 85%, and cycle efficiency also given to you. This is compressor efficiency. You have to find the isentropic efficiency of the turbine first, then mass flow rate. So in order to, let's how to do question quickly, let's see that also. So you have to find the turbine efficiency, isentropic efficiency of the turbine. So what is the isentropic efficiency of the turbine? So it will be actual by ideal, because actual work is less, because you are getting the work. So you have to associate your isentropic efficiency with the loss. So it will be T3 minus T4 dash divided by T3 minus T4. So in order to obtain this, you have to find T4 and T4 dash. You have to find T4 and T4 dash. So let's just first do that. So in order to find T4 and T4 dash, we have to use this equation because T4 dash is here. T4 dash is here. Yes or no? Yes or no? Tell me. Okay. So firstly, let's just calculate what can be easily calculated with us. So can we calculate T2? Can we calculate T2? Because in order to get T4 dash from here, in order to get T4 dash, T3 is given to you. T3 is given to you. Okay. T1 is given to you. T3 is given to you. So you require T2 dash. If you have T2 dash, you can have your T4 dash. If you have T2 dash, you can have your T4 dash. Yes or no? Yes or no? Yes or no? Yes or no? Okay. Okay. So from here, firstly, if we want to have our T4 dash, you require to find this T2 dash. So let me put a red tick here. I will make it blue once we will find it. So how we will find it? We know that as the process 1 to 2 is isentropic, we can apply this relation. 1 to 2 is isentropic, we can apply this relation. T2 by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma to the power gamma minus 1 by gamma. So we can find our T2 here. We can find our T2 here. So let's see what is T2. So if we find our T2 here, we have the value of T1, we have the value of P2, we have the value of P1, or we can say we have the ratio of it, or we can say we have the ratio of it, or we can say we have the ratio of it. Okay, now. So we can say we have the ratio of it. So whatever we may want to say, we will say it from here. If you get the T2 value, if you want the T2 value, so this T2 value will come out to be, let's see it. Can anybody tell me the value of T2? Can anybody tell me the value of T2, please? So T2 is coming out to be 488.87. Those who are live can cross check with me. I already have solved this question so that I can quickly tell you all this. So this T2 is 488.87 Kelvin. So once you have T2, you know what is compressor efficiency. We have said it. So compressor efficiency will be ideal upon actual, because here actual work will be more. So how we can write it? We can write it like T2 minus T1 upon T2 dash minus T1, T2 minus T1 upon T2 dash minus T1. Now we have the value of this. We have the value of this. Now we have the value of this. We have the value of this. Can we find the T2 dash? Can we find the T2 dash? So most certainly you will say that yes, we can find it. So you can please cross check it. So it is coming out to be 523.43 Kelvin. It is coming out to be 523.43 Kelvin. All right. It is coming out to be 523.43 Kelvin. Is that clear or not? So now we have this value of T2 dash as well. So can I put a red tick here? Can I put a green tick here? So yes, sir, you can. You will say like this. So T2 dash, I am putting a green mark here. So now we have all these values. Now we will find this T4 dash here. We can find the T4 dash because cycle efficiency is given to be 20%. So it is 0.2. You place all these values. You will have your T4 dash, and T4 dash will come out to be, if somebody can tell me, it is coming out to be 732.65 Kelvin. It is coming out to be 732.65 Kelvin. Now here you have the value of T3, you have the value of T4 dash. Now you have the value of T3. So now you require T4. So now see, T3 to T4 is isentropic, right? T3 to T4 is isentropic, right? So pressure ratio is given to us. So 6 gamma to the power gamma minus 1. So here we have the value of T3. T3, which is 1073 Kelvin. So we can have the value of T4 from here. We can have the value of T4 from here. We can have the value of T4 from here, and it is coming out to be 643. It is coming out to be 643.088 Kelvin. You can cross check with me. So now we have this value of T4. We can put all these value here, and we will get our turbine efficiency. So this turbine efficiency is coming out to be 79.16%. This turbine efficiency is coming out to be 79.16%. This turbine efficiency is coming out to be 79.16%. All right. All right. Now, what else we have to find? We have to find the mass flow rate. We have to find the mass flow rate. So we have been given power. So power is equal to m dot WT actual minus W compressor actual. Okay. So we can do this like this, that power is given 1500 kilowatt, 1500 kilowatt, 1500 kilowatt. So let's put 1500 here, 1500 here. Okay. We will have, since nothing is given about CP, okay, so we will consider air, nothing is given about CPCV, so we will consider CPCV gamma as constant, and we will put the value of CP here. So CP is 1.005 kilojoule per kg Kelvin. So as I have written it in kilojoule per kg Kelvin, you have to write it in kilowatt only. So this actual turbine work is what? Actual turbine work is T3 minus T4 dash. So you have now T3, you also have T4 dash, you have also T4 dash. All right. Minus compressor work. Compressor actual work is what? Minus T2 dash minus T1. This is our compressor work. This is our compressor work. This is our compressor work. So from here you have all the temperatures. You have all the temperatures. So only one thing will be missing, that is m dot mass flow rate. So you can calculate it, and it will come out to be somewhat near 13.57 kg per second. So is this question clear? Is this question clear? How to use the isentropic efficiency? How to use the isentropic efficiency? Tell me, is that clear or not? Tell me, is that clear or not? Tell me, is that clear or not? Those who are live here can tell me that. If it is clear or not, those who are live here can tell me that. Those who are live can respond to me. Now let's do one more question. Let's do one more question. Now here is one more question on your screen. I will take a pause here so that all the students who are live can attempt. So if the previous clear question is clear, can you tell me? And please start solving this question also. In this, combustion efficiency is also given. So let's just apply the concepts we have learned in this, not completely actual but partially actual cycle. Not completely actual but partially actual cycle. Can you do that, please? Can you do that, please? Just try to do that. Just try to do that. You have to find air fuel ratio here. You have to find air fuel ratio here. Please do it. I am taking a pause here so that the live students can do. So now if I go on reading this question, So find the required air fuel ratio in a gas turbine. Find the required air fuel ratio in a gas turbine whose turbine and compressor efficiencies are 85% and 80% respectively. Whose turbine and compressor efficiencies are 85% and 80% respectively. So let's just observe the data what is given to us. So we are given with the compressor efficiency as 85%, and we have given the turbine isentropic efficiency as 80%. The maximum cycle temperature, that is T3, is 875 degree Celsius. So we can certainly convert it. We can convert it into Kelvin. So it is 1148. It is 1148 Kelvin. All right. All right. The working fluid can be taken as air Cp, and this K is nothing but the gamma. Nothing but the gamma. Compressor inlet condition. Compressor inlet condition is 1 bar. So what is given? P1 is given. T1 is also given 27 degrees. So 273 plus 27, that is 300 Kelvin, and the pressure ratio is 4. So Rp is also given to you as 4. The calorific value is 42 megajoule per kg. So this is normally lower calorific value, or you may take only calorific value. Doesn't matter. And there is 10% loss of calorific value in the combustion chamber. So if 10% is lost, so what will be your combustion efficiency? It will be 90%. It will be 90%. And you require to find the mass air fuel ratio. You are required to find the air fuel ratio. Now, firstly, tell me this. We have seen this combustion thing now. We have seen this combustion thing, right? So now we have these two formulas. One is highlighted with the yellow ink, and one is highlighted with now this green ink, or green highlighter, we may say. Okay. Now tell me which equation we are going to use in this question, the green one or the yellow one. Green one or yellow one. So how we can observe if CPCV not changing. So in this question you can see that CP, nothing is mentioned like that CP and CV or gamma is changing with temperature or not. So we will consider that they are not changing. We may consider that they are not changing. So we are going to use the exact solution in which we have considered that CPCV gamma is not changing, and we have followed this air standard assumption. Got my point or not? We have followed the air standard assumption. Okay. So if I use that exact solution, I hope you all are getting my point. So if we use that exact solution, we have m dot f into calorific value into combustion efficiency is equal to m dot a Cp T3 minus T2. This is what we have written over there, no? Okay, where m dot a is the mass flow rate of air, m dot f is the mass flow rate of fuel. Okay, so where here we have to get the air fuel ratio, so do not make mistake. We want to have m dot a upon m dot f, but here this must be T2 dash, no? That is why I say always prepare the cycle. This must be T2 dash because isentropic efficiency is given. So now try to understand this. We have this TS diagram. Let's make that TS diagram. So sometimes mistakes can happen when all the things are combined together. So here combustion efficiency, isentropic efficiency are combined. So now since there is combustion efficiency, since there is isentropic efficiency of compressor, the entry, as we have seen in the previous question also, entry to the combustion chamber. This is our combustion chamber. Now, if you see the TS diagram, you will say that sir, in combustion chamber, the entry is taking place at 2 dash and exit is at 3 point. So here it must be T3 minus T2 dash. T3 minus T2 dash. Now for m dot A is equal to m dot upon m dot F will be from this equation will be equal to CV into combustion efficiency, CV into combustion efficiency divided by CP T3 minus T2 dash divided by 3P T3 minus T2 dash. T3 minus not a square, T3 minus T2 dash. Got this or not? Got this point or not? Tell me, got this point or not? Okay. Okay, so here again we are going to follow the same procedure. So we have this lower calorific value, we are writing it as LCV, don't worry. So we are having this value, we are having this value, we are having the CP. Do we have T3? So yes, we have T3 also. So if we can somewhat find the T2 dash, this is missing. This is missing. We will be finding this air fuel ratio. We will be finding the air fuel ratio. So from when, how we will be able to find that? So for that, compressor efficiency is given to us. Isentropic efficiency of compressor is given to us. So if I take compressor efficiency, so in compressor efficiency, what happens? What happens? That ideal is less, actual is more. So actual will be in denominator. So T2 dash minus T1. So now here, what you are having T1, you are having T1, but do you have T2? No, we do not have T2. So for finding this T2, so let me put a red mark here. We have this. So in order to find this T2 dash, we need to find this T2. Very simple, very simple. So one equation will lead to other. So if you first go on, sometimes what people do that they go and find all the temperatures first, then they come back to the question. So in this question, T4 is not required. In order to answer this question, why we will calculate the T4? We do not require it. So do not waste your time in these kind of things. Just write first what you have to find ultimately and see what is missing, what is not missing, and how to get it. It will help you in solving the question, especially in cycle. So we have this pressure ratio with us. So we know we have already used it in multiple times. So we have 4 gamma minus 1 by gamma here. So we can calculate our T2 from here. So T2 is coming out to be 445.79 from here because we have already the value of T1. Now we will putting it in this equation. So now this red ink I can remove and we can have our green ink back here. So we have now the value of T2. So we can find the value of T2 dash also. So it will be 482.24. Now if you have the T2 dash value, I can take away this red ink and replace it with green signal. Okay, so now in this equation we have all these values. Can you place them and can you get me the answer? So when you place it and when you calculate, your answer will come out to be 56.77. Your answer will come out to be 56.77. So those who are live in this session can respond. Are they able to get it or not? Tell me. Are they able to get it or not? Tell me that. Is that clear or not? We have somewhat moved into this. Yes, Vijay, somewhat nearby this answer, 56.77. Aishwarya is getting exact answer, 56.77. Okay. Now, you guys have able to see this. So we have moved somewhat to some extent from ideal condition to the actual condition in which we have now considered the combustion efficiency. We have now considered the isentropic efficiency. We have now considered the isentropic efficiency. Now listen to me carefully. From this question, it must be very clear that when to use which formula. This formula we have used in this question. Since CPCV gamma was not changing with temperature, but if CPCV gamma is changing with temperature, we have to apply the exact solution. We have to use the exact solution. So we are going to see that also. But before that, but before that, before that, but before that, we need to see some more practical things. So in practical, we have some mechanical losses. We also have some mechanical losses, due to which one new efficiency can come into picture, which we call as mechanical efficiency, which we may call as mechanical efficiency. So what happens? What happens, as we have already discussed all these things? So we have a compressor. We have a compressor with us. We have a combustion chamber with us. This is the major components of a gas turbine cycle: a compressor, a combustion chamber, a gas turbine, okay? And in open cycle, there is no cooler. Open cycle, there is no cooler. So now what is happening? What is happening here? So as I told you, if let's say gas turbine is creating WT work. So let's, for instance, let us take 250 kilowatt it is generating. 250 kilowatt it is generating. And to run this compressor, we require 100 kilowatt. 100 kilowatt. So till now in ideal cycle, what we were considering, that there will be no losses. When this 100 kilowatt, goes from turbine to compressor. But in actual, since this power flows from one place to another due to friction and due to practical consideration, there will be some losses. So what will happen? If 100 kilowatt, is to be reached here, you must give from turbine, you must give from turbine, hello Sunil, you must give from turbine for say 110 kilowatt. Something extra you must give. Okay, something extra you must give here. Okay, because since from this place to this place, energy will be lost during this transmission. Some energy will be lost due to frictional effect, due to all other effects. Yes or no? So although you require 100 kilowatt, at the compressor, but you must take out 110 kilowatt from the turbine to be sent to the compressor. So work net, what we see till now, WT minus WC. So in general, in ideal cycle, what we do, if this is 250, this is 100, we will say it as 150 kilowatt. So this we are using this thing in ideal condition, where though no mechanical losses are being considered. So this is our work net in ideal situation. But what happens here now? What happens in actual conditions now? That what net work you will get. So in turbine, you must subtract the work you are extracting for sending to the compressor purpose. So I will call it as WC turbine. So this will be 140 kilowatt. So this will be the condition in actual circumstances, in actual working cycle. Not turbine minus compressor is your network output, but your network output is somewhat more reduced because of this mechanical losses, because of this frictional losses, due to which this mechanical efficiency comes into play. So this mechanical efficiency is what? This mechanical efficiency is WC, what is required by the compressor, and what are you sending from the turbine. I hope it would be clear to you that what is required to the compressor, and what are you sending from the turbine so that the requirement of the compressor will be fulfilled. So in this case, you can say, in particular, in this example, can you say that our mechanical losses is 10 kilowatt, because 10 kilowatt is getting lost from this place to this place. So if mechanical losses is given to you, can you calculate WC turbine? Yes or no? I think you can. I think you can. So your mechanical efficiency, what is going to be your mechanical efficiency? So your mechanical efficiency is WC upon WC turbine, means what work is required at the compressor, and what divided by what are you sending from the turbine? What are you sending from the turbine? So if I replace this over here, if I replace this thing over here, so W net will be WT minus WC upon mechanical efficiency. We can do like this or not? So whenever mechanical efficiency is given, you can apply it like this. Whenever mechanical efficiency is given, you can apply it like this. Okay? Okay? If generator efficiency is also given, now you see, in generator also there will be some losses. Okay. So in generator, what power you are sending? This is the power created in the generator, and this is what W net. So both units must be same. If you are putting it into the megawatt, you must putting it into megawatt 2. You are putting it into the megawatt 2. So this is what network, this network, see this and this are going to be same. So if generator efficiency, these two are same only. If generator efficiency you are asked or given, you can do that. This is the power which is ultimately going outside of the plant, which is in the form of electricity created by the generator. So if generator efficiency is given, you can calculate your W net in megawatt, or vice versa from here also. Okay. So one more losses is left. I will complete that, and then we'll move towards a question. Okay. So I will move towards the question. Finally, I will conclude all this session first, and then we'll go to the question. One final question of this series. I hope all of you have enjoyed, who have attended the live session as well as seen the recorded video. All of you have enjoyed. So one last practical or actual considerations, consideration is pressure losses during actual gas turbine cycle. Pressure losses. So just it is not numerically very rare. Pressure losses will be given, so I am not going to put that into numerical. Okay. So pressure losses during actual turbine cycle. So see what devices we have considered as constant pressure. So we have considered combustion chamber as constant pressure. Combustion chamber we have considered combustion chamber to be constant pressure device. So in practically, it is not actually constant, works at constant pressure, but there will be some pressure variations in practical condition. What else we have considered? I am talking about open cycle here. Not closed cycle. Closed cycle cooler is just be placed just to help us to make PV or TS diagram. That's it. Nothing else. What else? So regenerator we have seen, which is a heat exchanger only. So heat exchanger is generally, if you see the definition of a heat exchanger in some heat and mass transfer book, heat exchangers are always constant pressure devices, but that is not actually true. Some pressure losses will take place there also. So if pressure losses happen, they happen where we have considered the constant pressure things, So now let's try to understand this. Numerically, we are not going to see it because it is very less tentative that it will come in the examination. But although for more factor of safety, you can go and see it. So let's just try to understand the facts here. So we have, in ideal condition, we have this 1 to 2. Then if regenerator is there, it will go to this point A somewhat, okay? Then it will go to this point 3. Okay, now forget that 4, sir. In this case, 4 is not about T. Let me do that also, no problem. Okay, so this is somewhere our 4 is still not looking like that. Just consider that 4 is above 2. Not, this is not the point. We already have explained these things in the previous session. Okay, so it will go to 3 to 4, then it will come to B, and then it will come to A. So if the pressure losses are there, so there will be a pressure loss at this place. So when your air exits from this regenerator, actually the pressure line will change. Here. Say yes or no. Actually, the pressure line is going to get changed there. Yes or no? Tell me. Yes or no? Tell me. Because pressure will be reduced. Okay. Now in combustion chamber, it want to go like this. But at the end of the combustion chamber, which is also a constant pressure device. So your pressure will reach here at 3 dash point. Will come here at this 3 dash point. Got my point or not? Tell me, got my point or not? So just expanding a bit. So it is far too much expanded. Let me go back. So now little bit we can manage from here. So see, if in a combustion chamber also pressure loss is happening, so there will be one more pressure loss. So this red pen pressure loss will be in combustion chamber. This blue pen pressure loss will be in regenerator. So what actually will happen? Before entering to the turbine, the pressure will be reduced. So definitely we are not going to get that output with what we are getting without the pressure loss. So what will happen? So it will expand, and then will go into the regenerator. But there is some losses going to happen, pressure losses going to happen in 4 to B section also. So if we expand in the turbine at till this point 4, and further reduction of pressure happens, then our one cycle will not be completed. So what we do, if this is 1 bar, and there is 0.25 bar, let's say there is 0.25 bar is going to get lost in the regenerator section. So we expand it not to 1 bar but to 1.25 bar, so that in regenerator this point can be reached, this B point can be reached, and you can complete your cycle. So simply the pressure losses, if there are pressure losses, your output, your specific work output in the turbine will certainly is going to be decreased. But generally in calculations we avoid it. We usually avoid it. So here is a question that I want you to solve. This will be the last question we are going to solve. So I have written some data of it. I have typed some part of it and also have written some data to it. So this question on your screen, this is the question on your screen. This black pen is the given data. This black pen is the given data to you. This black pen is the given data to you. So I hope all of you can see this question correctly. All of you can see this question correctly. Okay. So please start to solve it. Please try to solve it. Please try to solve it. All right. Please try to solve it. I will take a pause of 3-4 minutes here so that the live students can solve this question. Okay. So this is gonna be last question in this series. I hope all of you who have watched all the sessions, this is the 12th lecture in this steam turbine and gas turbine series. So in this 12th lecture, not only we have covered the steam turbine and gas turbine, we have covered the compressible flow, we have covered the already added part of gas turbine cycle, we have covered new part also. So if you spend your 24 hours watching this video, you will be having a lot of benefit. You will be having a lot of benefit. Okay. So please, if you have watched all the session, or if you have liked this series, if you want such more kind of series to happen at the GATE Academy, do write to us, do comment in the comment section. Okay. Do comment, do like, do subscribe, do share, do refer to your friends also to watch these videos. Okay. Please try to solve this question. In this, except for the pressure losses, we have added everything. Except for the pressure losses, we have added everything. See, CPA, CPG, gamma G, everything is given. Gamma G, everything is given to you. Isentropic efficiency is given to you. Combustion efficiency is given to you. Mechanical efficiency is given to you. Generator efficiency is given to you. So almost everything we have added in this question except the pressure losses. If you want to solve the pressure losses question, you can refer Gas Turbine book written by Dr. Regeneration. It is a very good book, but I don't think that will be required. But even if you want to do that, you can do. As I always say, there is no guarantee in GATE examination. Whatever may come, you can, and we can try to cover it in all possible manners, but there is no limit. They can ask anything. Okay. Okay. But as you know, we cannot cover all the things. Since you can understand that Sir Regeneration sir has written a book only on gas turbines. So if we want to cover the gas turbine, there is this much book there. So data is everywhere. So many things are there. So we cannot cover each and everything. So for GATE point of view, whatever was necessary, we tried to cover. Okay, we tried to cover that. Now, can anybody will tell me the answer? Can anybody tell me the answer of it? Could anybody tell me the answer? Can anyone give me the answer? Can any of you can give me the answer, please? This is the last question we are going to discuss. We are going to see in this series. This is a very good series, I think. You can tell me your observations. So in the comment section now, you can see there is a link where you can find the notes of thermodynamics. So I will upload them. I will upload them. I will upload them after the completion of the session. Okay. Okay. So after this session, I will upload the notes. Please also like and subscribe. So whatever we have learned in this thermodynamic session, I will be uploading here. After the completion of the series, I will upload. So let us begin. Let me solve this question. Let me solve this question. So what is the data given in the question? We can see now. Now please observe. So a two-stage compressor with a intercooling. So we have intercooling cycle in between stages, and in a single turbine, regeneration is also there. Is used in an open cycle gas turbine. Open cycle is there. Open cycle is there. So as I said, this CPA CPG thing happens mostly in open cycle gas turbines. So air at 1 bar 15 degrees. So what is given? What is given? Let us write the given data. Or let us first make the cycle after reading the question. First thing what we do, we must make the TS diagram so that everything is in front of us. What is given, what is to be found, how to be found. So first let us prepare the TS diagram. So what is there? Regeneration is there, intercooling is there. Now see, isentropic efficiency is also there. Isentropic efficiency of turbine is there. Isentropic efficiency of both the compressors are given. So considering that, let us make the TS diagram. So I am solving the question. I have written the question with black ink. So I will be giving you the solution in the blue ink. So now let us see. Let us see. So in case of intercooling cycle with regeneration, we already had it done before. So we have three pressure lines. Firstly, since there is no pressure loss in the question, so we do not consider it. We will not be going to be considering it. So we have first stage compression. So let's say the first stage compression took place from 1 to 2. Then we had an intercooler, and you can see there's a technical issue. You have to just a second. Huh? Okay. Okay. Coming back to this. So we have, it is written that, see, assume perfect intercooling. So perfect intercooling, we already know what it is. We have seen, that is why I told you that understanding the ideal cycle firstly is important. Understanding the ideal cycle firstly is important. So now if you didn't know the perfect intercooling, how will you be able to solve it? So this is 1 to 2, 1 to 2, what is happening, 1 to 2, what is happening, 1 to 2, compression is happening. Then this is 1, 2 to 3, and as it is perfect intercooling, now you know that T3 will be equal to T1. So this is what data is given in the question. T3 is equal to T1. T3 is equal to T1. Okay. Okay. So this is firstly, I'm making the ideal cycle. So from 3 to 4, what is happening? From 3 to 4, what is happening? Again, second stage compression is taking place. Second stage compression is taking place. And now we are going to this T5. We are going to this T5. T5. We are going at this T5 5 point where heat addition takes place in the combustion chamber, and then we will expand to this temperature of 6, this point 6, and 6 is above 4, as you can see. So there is a scope of regeneration. If there is regeneration, the exit temperature of the turbine should be above the entry temperature to the combustion chamber. Otherwise regeneration will not be effective. This is what we have seen. Now, if we apply the concept of what we have seen of isentropic efficiency, so this must do what? This must go like increasing like this. This must go on and increase like this here. So it will be 2 dash here. It will be what? It will be what? It will be 4 dash here. And since there is a regenerator also, so from 4 dash, so regenerator will come into play between 4 dash to A and 6 to B. 6 to B. Yes or no? 6 to B. Tell me yes or no. Tell me yes or no. Okay. Okay. So we will apply this regenerator thing. Now remember, regenerator will do what? Now I am making a regenerator here so that no confusion will come to you. So from 6 to B, what is happening? from 6 to B, hot fluid is going, and from, or generally we put hot fluid upwards, no, so no problem, we'll put a hot, although it doesn't make any difference, but you follow the same procedure as we do. So this is 6B, this is 6 to B, and this is 4 dash. This is going from 4 dash to A. This is going from 4 dash to A. So let us draw like that. This is 4 dash to A. This is 4 dash to A. Okay, this is 4 dash to A. So our regenerator will play between these points. Now we have the isentropic efficiency of turbine also. So let's just put it there. So 6 dash. Now you see from here that we have this gas CPG gamma G is given. So it means that CPCV gamma changes with temperature. So at this point, beyond whatever we do beyond this point, beyond whatever we do here, we will take the properties of air. Okay, and once the working fluid exits from that combustion chamber, we will take the properties of gas. So we will take CPG gamma G after this 5 point, and we will take CPA gamma A before entering to the combustion chamber. Okay, understanding the question or not? This is the TS diagram. This is the understanding of what we are having. So much data is given to you. So in this kind of question where so much data is given to you, it is always beneficial to strike whatever we have to find. Now see what we have to find. We have to find air fuel ratio. So if we have to find air fuel ratio, we have to apply the energy balance between combustion chamber. Energy balance we have to do of the combustion chamber. So entry to combustion chamber is at 4 dash. Entry to combustion chamber is at 4 dash, and exit to combustion chamber is at 5. Exit to combustion chamber is at 5. Is that right or not? Tell me, is that right or not? Getting my point or not? So entry to the combustion chamber is at, sorry, not at 4 dash, but at A, because regenerator is also there. Na? So entry to the combustion chamber is at A, and exit is at 5. So now tell me which equation we must use, exact one or approximate one. Which equation? We have seen it today, no? So this yellow ink equation we must use, or green ink equation we must use? Tell me that. So we must use this exact solution, because as I have told you, whenever the changes of CP, CV, gamma is given to you, you must use your exact solution. So from this question, it is also must be clear to you that when to use exact solution, and when to use the approximate solution. So we have already used the approximate solution. So here I should do what? I should use the exact solution. So just I am removing this highlighted part, and this T3. So the entry, this must be T5, because this is the condition of 5. So here it will become a gas, and before it was a air. So here you must write TA. Now, in order to get your air fuel ratio, what is you are having, what you not having. So let's check lower calorific value. So yes, we have the lower calorific value. So put a green mark. We have the combustion efficiency. Put a green mark here. Okay, same way we are doing. If by using this approach, you will find it quite nicer, that solving numerical will become easy. So this is the lower calorific value. So we have put a red, green tick there. Combustion efficiency we are having, so we have put a green tick there also. We have this CPG. So we are putting green tick there also. We are putting green tick there also. So do we have m dot a? So I think we have this m dot a also. Let's see. Let's see. So yes, m dot a is also given 250 kg per second. So m dot a is with you. So CPA is there with you. So what you require? What you require? You want to find m dot f from here, because once you can find m dot sorry, once you can find m dot f, you can have your air fuel ratio. So what do you require to find m dot f? So you require one T5, you require one TA. You require T5, you require TA. So for T5, T5C, maximum temperature in the cycle is 800 degrees. So T5 is already given to you. Now T5 is already given to you. So let us put a green mark here as well. T5 is given to you. The maximum temperature in the cycle is 800. 800 plus 273. So T5 is given. T5 is given. T5 is given is 1073 Kelvin. So now you must try to find TA, and you will be able to find your air fuel ratio. So how we can find TA? So we have to, for TA, we require T4 dash. Yes or no? This C, see this effectiveness is given to you. Effectiveness is given to you. So if effectiveness is given to you, you can write like this: effectiveness is equal to TA minus T5 divided by TA minus T5 divided by T6. Okay, this is how we do it now. T6, not T6, but T6 dash, because entry to this is from T6 dash, because isentropic efficiency of the turbine is also given. So this 6 dash is actually the exit of the turbine from where the exhaust gas is going into the regenerator. So you require T6 dash also. Okay, minus T5 minus sorry, this is not T5 but T4. T5 is the last temperature, no? So this is T4. So this is T6 dash minus T4. This is T6 dash minus T4. Got my point or not? Got my point or not? Tell me, got my point or not? Okay. Okay. So this is T4 dash again, because since the exit to the compressor is at 4 dash. See, so many data is there. Okay. So don't get confused. Okay. So from here, if you want to have TA, now see what is given, what not is given. This is given. Rest we have to find. So now, can we find T2 dash? How we are going to find all these things? So we know that T2 by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma. So you have the value of T1, you have the pressure, you have, now see here what data is given. Maximum pressure ratio is 5. Maximum pressure ratio is 5. Okay. And the case is perfect intercooling. So in case of perfect intercooling, you know, the intermediate pressure will become under root of PHPL. We have derived it, no? PHPL. So what we can do here? If we use the condition of perfect intercooling, you will come to know that, sir, we can use this, because P2 will be under root P1 and P4, high pressure, low pressure. Okay, we have developed this in the previous session. So from here, you have this T1, you have this pressure ratio PH by PL, that is 5. So you can have, this is under root 5, and you have the value of gamma. Or here, this is what gamma A is there, because you are seeing it before on the left of this line. So we have this value of gamma 1.4 minus 1 upon 1.4. You have your value of T1. So can you find T2 from here? Tell me, can you find T2 from here? So this T2 is coming out from here is Aishwarya, you have calculated wrongly. So this is coming out to be as 362.44 Kelvin, 362.44 Kelvin. Now you are given with the compressor efficiency of 1. You are given with the compressor efficiency of 1. So compressor efficiency of 1, if we apply, so you will say, sir, it is very easy. We already have seen it separately. So you have to do ideal upon actual. So T2 minus T1 upon T2 dash minus T1. So let me just highlight the temperature values so that we can use in the future also. So now we have this T2, we have this T2, we have this T1. Can we find our T2 dash here? Can we find our T2 dash here? So T2 dash, if you find from here, it will be 381. You can calculate the values with me. Those live students can calculate the values with me. So since it is a case of perfect intercooling, can we say that T4 dash is also same? You can cross check by applying the efficiency of the second compressor also. But in this case, since two things are there, since it is perfect intercooling also these two are equal. These two compressor efficiencies are equal. So if you go on and finding T4 dash, it will come out exactly be equal to T2 dash. It will come out to be exactly equal to T2 dash. So now you have the value of T2 dash, T4 dash. You have the value of T2 dash, T4 dash. So why we were doing all this? Because we want TA. We want TA. So now you have the value of T4 dash. You have the value of T4 dash. Now you require T6 dash. Once you get T6 dash, you can get TA and you can put it in your this equation of the combustion chamber equation, and you can have your mass flow rate. So now can we say like this? Can we say like this that T5 by T6 is 5 to the power. Now see, I am putting from 5 to 6. So firstly, highest pressure ratio is applicable because you are going from the topmost pressure to the bottommost pressure. Topmost pressure to the bottommost pressure. So this is going to be 5. And what you are going to use here? You are going to use the value of gamma G here because as I have told you that after this reason, after our working fluid leaves the combustion chamber, you can no more use the properties of the air because gamma, Cp, etc. changing with temperature. So from here you have the value of T5 given in the question, highest temperature in the cycle, 800 degrees Celsius, that is 1073 Kelvin. So from here you can calculate. From here you can calculate your T6, and your T6 is coming out to be, can someone tell me the value of T6? So it is coming out to be 719.7 Kelvin. 719.7 Kelvin. Is that okay? Please check and tell me. This is coming out to be 719.7 Kelvin. If you put gamma G is equal to 1.33. Remember this, you have to put gamma G is equal to 1.33 as given in the question. Now moving ahead, what we require? We require T6 dash. So turbine efficiency is given to you. So turbine efficiency is what? T5 actual, because actual is less in this case. So T5 minus T6 dash upon T5 minus T6. Ideal is more. Okay. So from this equation you have this turbine efficiency, you have this T5, you have T6. So from here you can calculate your T6 dash. So your T6 dash is coming to be 755 Kelvin. Okay. So you have now the value of T6 dash also. Now moving up to this equation. Now you have all the values required. Now you have T6 dash also. So can you find your TA from here? So you will say, sir, definitely we can find. So if you find the TA, it will come out to be 642.8 Kelvin. Now, once you have TA, can you put it back into this equation? So can I remove this red tick now? So if I remove this red tick now, you have this value, and from here you can calculate the mass flow rate. you can calculate the mass flow rate. So just I'm copying this equation. I am copying this equation and bringing it here. Okay. So now we have this all the values. So from here we can certainly find the mass flow rate of the fuel. We can certainly find the mass flow rate of the fuel, and it will be 3.309 kg per second. 3.309 kg per second. So how we did it? Is that clear or not? Is that clear or not? And once you have your fuel ratio, mass flow rate of fuel, you can definitely find this air fuel ratio. So do it by yourself. So let us go to the cycle efficiency. So for cycle efficiency, we require, what is cycle efficiency? Now see here, please pay attention. So the cycle efficiency will be net work done upon the net heat added. We know it, no? So what is the net work done here? What is the net work done here? So net work done will be the net work done by the turbine. Net work done by the turbine. Got it? Got it? Okay. Minus, or let's say, let's just do like this. Let's just do like this. Now see. Firstly, let's try to separately find the compressor work. So we have compressor 1, we have compressor 2. So since it is a perfect intercooling, we can say WC1 is equal to WC2. Okay, so net compressor work will be 2 times WC1. 2 times WC1. So this net compressor work will be 2 times. So let us go and watch our TS diagram. So this WC1, this WC1, this WC1, this WC1 is going to be T2 dash minus T1. So I assume you have calculated already all the temperatures, so you can solve it. So if you put this value and where we have to use CPA because it is before the combustion chamber. So if we calculate it and we have the value of m dot A also, so let us directly calculate in kilowatt or megawatt in form of power. So it will come out to be 46.7. It will come out to be 46.7 megawatt. Okay, I hope you can put the values of temperature and calculate. We have all the values. Okay, so we have combined compressor work is 46.7. Now what is the net work done? What is the net work done is equal to our turbine work. We have developed this equation. Since mechanical efficiency is also given, okay, so this is the work generated by the turbine, but the net work is WT minus WC upon mechanical efficiency. We just have seen it. So what is this WT? This is the work generated by the turbine. So now see, turbine produces work. If you see the diagram, it is from 5 to 6 dash. So it is after combustion chamber. If it is after combustion chamber, so we have to apply the concept we have learned. So here we are going to use the mass flow rate now will be equal to m dot. Very, very important this is. So turbine work, if please pay attention, very, very important this is. So turbine work you are calculating, so you have to calculate like this. So the mass flow rate is now m dot A plus m dot F, and the specific heat is now SPG, CPG, and the temperature difference is T6 minus T7 dash. Please pay attention, please see carefully. Why we are using m dot A, just a moment. Why we are seeing this m dot A? Why we are taking this m dot A plus m dot F? Because here you see the 5 to 6 dash stage is in the gas side. So we have to use the combined mass flow rate. We have to use combined mass flow rate of air and the fuel. Okay. So we will use this formula here. We are going to use this formula here. And we have all these values. We have calculated all these things. we have calculated all these things. And let me tell you, this is very, very important. People might make mistakes here. That is why I took this much big question, so that everything will be covered in a single question, and actual gas turbine cycle will be clear to you. Clear to you. So from this, if you put all the values, we will be getting 86.99 megawatt. We will be getting 86.99 megawatt. And if you put all these value in the work net, mechanical efficiency is given to us. Now see the question. Mechanical efficiency is given to us where it is. Mechanical efficiency is 96%. Mechanical efficiency is 96%. So if you put the value of mechanical efficiency and everything, the net work you are going to get is 38.32 megawatt. So this work you have obtained by considering the mechanical efficiency also, Now we have the work net, so we have to find the heat addition. We have to find the net heat addition. Okay. So whatever you feel comfortable in, either you can use this part. This is also the net heat addition, and this is also the net heat addition. Okay. You are just balancing the energy. Okay. So either you use this, So my mind is telling me I should use the simpler equation. So I will use heat addition, the net heat addition, like m dot f, calorific value we have, combustion efficiency we have. So we can have our net heat addition. So if you do this, you will have this heat addition. You will put all the values. You will have 132.02 megawatt. So now the cycle efficiency will be what? What will be the combined cycle efficiency? So if you put the value of W net you have derived, and you put the value of heat addition you have got, so it will come out to be 28.99%. It will come out to be 28.99%. Got it or not? Okay. So in the last, what is given? Power supplied by the plant. It is asked to us, what is the power supplied by the plant? So very simply, generator efficiency is given to you. So we have seen the power supplied by the plant. Generator efficiency is the net power supplied by the plant, including generator and everything, divided by what we get from the turbine. So this is what we are getting from the turbine. We have already have this value. So we can calculate the value of P as well from here. So I think this question I can leave from here. From here you can multiply. Your generator efficiency is given to you. Your net work from the turbine you already have calculated. So you can find your power from here. So actual gas turbine, is that clear or not? We have completed the actual gas turbine part. Is that clear or not? So let's quickly, let me conclude this series. So what we have seen till now in gas turbine. Okay, so in gas turbine, so if actual cycle is clear to all of you, the students who are live can respond to me. In this particular question, I have applied everything what I have taught to you in gas turbine cycle. Okay, ideal is applied, actual is applied, everything is applied. Isentropic efficiency is there, everything is there. Yes or no? Okay. So moving ahead, components. What are the components of gas turbine? So in a gas turbine, we know we had a compressor. Now see, this was already there in the GATE syllabus. It was added from GATE 2016. So this you have to cover by yourself because it was already there in the GATE previous year syllabus. Okay. So compressors are of two kinds as respect to the gas turbine. One is axial flow and other is centrifugal. other is centrifugal. So, so from the previous syllabus, I hope you already have covered it. You already have covered it. So this compressor part is already been covered in all previous GATE syllabus. The other thing is combustion chamber. So you know, you have seen how combustion chamber do it. As the equipment, I don't feel you should study it because it's completely theoretical thing, that this is there, duct is there, and this that. So this is not required to be studied according to me. Overall, you know the purpose of this combustion chamber, that heat is added, fuel is getting burned, combustion efficiency is there, this that, lower calorific value is there. So this is covered. Now the third component was gas turbine, which in GATE syllabus is written specifically. So gas turbine is a axial flow turbine. So about the axial flow turbine, we have seen all the things which is required in this session. It is an axial flow turbine. We have seen all the things required about axial flow turbine in this lecture series. Just go and watch all the lectures. You will find everything about axial flow turbine. So nothing more I want to say about this gas turbine. Okay, everything what I have taught is applicable to the gas turbine also. Just one thing, that these are lighter as compared to the steam turbines. Major difference I am highlighting here. So these are lighter and have more stages. And have more stages. Have more stages in general. Have more stages in general. So if you watch all the sessions, if you have watched all the sessions, or if you will watch all the session, you will find how to deal with this stage thing. Okay, so nothing again to be taught more. Okay, one last thing is vortex bleeding. One last thing what we generally use in gas turbine is vortex bleeding. So vortex bleeding is refers to the twisted blades. Vortex bleeding means that we are making twisted blades. Okay, and why we are doing it? Why we are doing it? We are we are doing it because we want to decrease fluid flow losses. We want to decrease fluid flow losses. We want to decrease fluid flow losses. Okay, so this much one objective question can come, that where can vortex bleeding is useful. So it is required, it is used to decrease the fluid flow losses. So this is all what I wanted to teach you in this live series of steam turbine and gas turbine. In steam turbine and gas turbine. So I think we at the GATE Academy have comprehensively covered all the new addition into GATE 2021 examination. Okay, so you can send your feedbacks to us. Okay, you can tell us your feedback, your suggestions, whether you liked it or not, whether this series was useful to you or not, have you enjoyed it or not, you liked it or not, whatever came here, whatever come here. Okay, whatever things we have discussed here is clear to you or not, you can tell me into the comment section. Your feedbacks are very, very important. So hereby, to the live students, I am asking, if there is a doubt, they can ask me. Otherwise, we will end this 12 session long, 24 hours series of gas turbine and steam turbine, which is newly added topic, into the GATE syllabus 2021, into the GATE syllabus of 2021. So the students who are live can respond to me. Thank you, Anand. I hope you all liked and you felt that this series is useful for you. It will help in your GATE preparation. Okay. So with this, thank you very, very much, and best of luck to all of you, and best of luck to all of you, all of my students, and the students of the GATE Academy, or every student who is watching this video or not even not watching this video. Okay, to all the students of mechanical engineering, very, very best of luck. Very, very best of luck to you guys. I hope you will get very good marks in your GATE 2021 examination, and you will be into some PSU or an IIT. Okay. So thank you very much. Thank you all. Your notes will be uploaded in this website. So please like, subscribe the GATE Academy English channel. The GATE Academy English channel. You can provide your feedbacks on this mail ID you can see on your screen. You can call us. You can visit our website. Okay. So finally, thank you very much. Best of luck. Study well, prepare well, and do subscribe the GATE Academy channel. Thank you.